Probably the first thing you want to do with a problem like this is draw a diagram. So here's our spring, and we can say that our spring is being pulled out. At some point here, we have our equilibrium position. I'm just going to say that that is EQ. And that equilibrium position is where our X would be 0. In this case, it says that the spring is being pulled a distance of 0.750 meters right from equilibrium. So that means that this distance right here is 0.750 meters, and it's being pulled to the right. So we can add our forces here, and we can say from this spot right here, we have two different forces. We have our force applied, so I'm just going to say that that is our A. And then in the opposite direction, we have our FR. And our FR is known as our restoring force. We also want to indicate that we have positive to the right and negative to the left. Last thing that the question tells us is that we have our spring constant, which is 42.0 newtons per meter. We're going to use Hooke's law, and we're putting a negative sign because the force is acting, the restoring force is opposite to our force applied. We're doing our negative spring constant multiplied by our x, which is 0.750 meters. Our answer here is negative 31.5 newtons. With this question, the first thing you want to do is draw a diagram again. We can say that if our spring was not attached to anything, this is where it would be sitting. When we have a mass attached to our spring, the question says it has a displacement of 0.4 meters. So we say here this is 0.4 meters. Because this spring is not moving and the mass is just hanging, we'll say our mass is this red thing right there, the mass is just hanging, we can say that right here this is our equilibrium position. And we know that at equilibrium, we know that our F net is going to be 0. We can also say that at equilibrium, we know that our Fs has to be equal in magnitude to our Fg. So we can say that these would be absolute values because they're equal in magnitude. If we want to draw our forces here acting on the mass, our free body diagram, we can say that this is going to be our Fg, and equal and opposite in magnitude, this is going to be our Fs. Okay, so from what we learned yesterday from Hooke's law, we know that our Fs has to be equal to our spring constant multiplied by the displacement. And that's a vector quantity. In this case, we can say that anything that's moving upwards is positive and anything that's moving downwards is negative. So we know that we're going to want our Fs to be positive and our Fg to be negative. We also know, as per usual, that our Fg is going to be equal to our mass times gravity. Because, like we said over here, where I'm underlining right now, we know that at an equilibrium position, our F net is going to be equal to 0, and these two are therefore going to be equal to each other. We can say that Fs is equal to Fg, and we can therefore say that Kx is equal to mg. Now what we're looking for is our spring constant, and we can solve for our spring constant. So we can rearrange this, and we can say that our K is equal to mg over x, and then we can plug in our numbers. From the question, it says that our mass is 785 grams. We need to turn that into kilograms. So we know that we have 0.785 kilograms. We're going to multiply this by our g, which is 9.81, and then we're going to divide it by our displacement. We want our displacement to be in meters, which it is, so we have 0.400 meters. We're going to get a final answer of 19.25 newtons per meter. For significant digits, we are going to turn that into 19.3 newtons per meter.